Okay. So in section 15.3, we're going to be talking about the energy of the simple harmonic oscillator, the mass spring system, or any type of oscillator that is in simple harmonic motion. SHO, simple harmonic oscillator. Now we know that total energy, as we just saw in the example questions, is the sum of kinetic and potential energy. So now what we're going to do is take the kinetic energy terms for the simple harmonic oscillator, the potential energy terms for the simple harmonic oscillator, and figure out what the expression is for the total energy of that system. You can use it in various different applications. We already know our expressions for position as functions of time of the oscillator, velocity is function of time, and acceleration is function of time. And then next, also today, we're going to look at velocity as a function of position, because we can figure out, based on where you are, positionally, we can figure out what your speed is, you know. And even so, your acceleration. Because remember, this is a gradient. You have maximum values and min values, well, max accelerations and max velocities, but they change. One is going towards a maximum and one is getting more and more minimum. One's going to zero. Let me guess. Kinetic energy goes to zero. The other one's going to a maximum, potential energy maximum. It's all it really is a synergy. So this is our basic thing, kinetic energy in terms of a linear object moving along a line, 1/2 mv squared. We know that, we got it. So velocity of a mass spring system or simple harmonic oscillator, we derived that last class. And so we're just going to substitute that expression. Right? Look familiar? The derivative of a cosine omega t plus phi, which is negative sine, or negative omega sine, chain rule action. And let's get the elastic potential energy of the spring. We've dealt with that before, 1/2 kx squared, right? They use the symbol U for potential energy. It's not to be confused or anything with the anything else, or it's just simple. A cosine omega t plus phi squared. Okay, right? And let me expand both of those. So I want to do it first, but anyway. So anyway, the kinetic energy here, 1/2 m omega squared a squared sine squared omega t plus phi. And then potential energy is going to just be 1/2 k a squared cosine squared omega t plus phi. Probably see where this is going. Sine squared plus cosine squared is 1. Total energy. So in simple terms, K plus U. Now again, this term, or omega squared, is K divided by M. We only get that from the solution of the differential equation for the spring, mass spring system. So we have md squared x dt squared equals the force of the spring. So basically, we get this expression by solving for the position function that we took for granted. But this is what omega squared is, and we're going to be using that here. So 1/2 Ka squared, just factoring out, sine squared omega t plus phi. Okay. And you know from trig that this goes to 1. Sine squared, you know, trig identity. Didn't think you'd use those again, right? But anyway, sine squared plus cosine squared is 1. And it could be any variable, x. If this is your x, this becomes 1. So the total energy of a simple harmonic oscillator is really the potential energy in effect. But yeah, so the total energy of a simple harmonic oscillator, 1/2 Ka squared. And that makes some physical sense because at the extremes, we have the maximum potential energy. So the maximum energy, it should be 1/2 Ka squared because at the, you know, we're talking about the energy as a function of amplitude, makes perfect sense. But this is what we get as a derivation. Any questions on that? So yeah, I think what I want to do is this. Nope. All right. So you guys will have that. So the total energy or total mechanical energy of a simple harmonic oscillator is a constant and related to its amplitude. I mean, we can see that clearly here. We know from conservation of energy, it's constant, and we see that it's related to the amplitude A. And we get to electrical engineering and you build radios, the volume of a signal is related to its amplitude. So how loud something is related to how large that wave is, the large amplitude. And you can modulate that amplitude, AM radio, to get a particular signal coming in from the broadcasting station. But intensity-wise, back to the point that your volume of your voice or sound or anything is related to the amplitude. How much energy are you packing into that wave? Well, corresponds to loudness or softness. Okay, so the potential energy maximum is maximum. We just went over this when x is plus minus a for amplitude, and the velocity is 0 at those same 2 points. Thus, kinetic energy equals 0 at plus minus a. So now what we want to do is find the velocity as a function of position. We know velocity is a function of time. We got that right up here. And go back to your previous notes, et cetera. Right? So we have that. So it's derivative of the position time function. Okay. Now let's find velocity. A little dust particle on screen here. Oh boy. Okay. All right. So let's find velocity as a function of position, that is v of x. Y of x, you've seen that a lot of times in math. Starting with E equals K plus U. Okay, that's 1/2 mv squared plus 1/2 kx squared. E equals, well, 1/2 ka squared. We just derived that. Oop. Right? So even though the total energy and the potential energy look similar, it is different because the amplitude is the maximums and x can be anywhere between those maxima. You know what I mean? It could be A or it could be anywhere else in between. That's why we have changes. This is a gradient. It rises and falls, but there's an interval between the energies, the times. So 1/2 cancels out. Right? Equals Ka squared. And so we want to solve for V. mv squared equals Ka squared minus Kx squared. K divided by M. And it's going to be for both of these K's. So we just factor out the K over M and we get A squared minus X squared and take the square root. V of X is equal to square root of K over M. So I can get my velocity at any position. But let's say if we go back to the previous example, the amplitude was 5, and then I want to find it at 2. Well, I can use this function here to find my velocity at 2 centimeters. And not just at the, well, at the edges. Let me go ahead and amend a previous statement. You can, well, right, I was saying, yeah, you can find the velocity at any other positions because at the amplitude it must be 0. Okay, velocity must be 0 at the amplitude. But this equation here allows you to find it at any position between the amplitudes. Doesn't have to just be 0. Oh, that's my max. Because that's your max. But what about if it's 3.7? Well, this allows you to do that. Or V of X equals, and square root of K over M is just omega because omega squared was K over M. So square root is omega. So this is going to be plus minus because, square root can be, 4 squared or -4. So it's plus minus. Square root of 4 could be plus minus 2. So plus minus omega A squared minus X squared. And obviously, when X is equal to 0, you have a maximum velocity, which we've been talking about. Plus minus omega A. So does that make sense? Any questions thereabouts? That's your Vmax. Okay, so now see if we have some time for examples there. But so our last section is 15.5. We're going to be looking at periods of 3 types of pendula. Plural of pendulum. So let's say that we had a regular pendulum, or, can I even write? Okay, let me draw. Okay, so now, all right, so I have, this guy, regular mass on the end of a string, goes back and forth. So period of a regular pendulum is period T, 2 pi L over G. So in looking at this equation here, the period of a pendulum only depends on its length, while acceleration due to gravity is going to be constant. It has nothing to do with its mass. So if I have the same length for two grams or 200,000 grams, if the length is the same, it'll have the same period. It'll oscillate back and forth in the same time. Again, another example of how the acceleration due to gravity has no bearing on mass. Okay, well, and then we have a period of a physical pendulum. It's basically taking that mass at the end of this string and making it a weird shape and swinging that back and forth. It has moment of inertia and all that good stuff. So if we have like, the center of mass is, arbitrary. It doesn't have to be in the quote center, it's somewhere. Okay? And we swing that guy back and forth. Then we can find its period by way of a differential equation. And we get up to 2 pi moment of inertia divided by mgd. Where I is moment of inertia. And that depends on moment of inertia, the mass of the physical pendulum, and gravity constant, and the distance of the center of mass from the pivot. If I have my bearing straight on that. Yeah, pretty much it. But in a problem, you know, we're be given that. But let me just in the time that we have, extrapolate on that a little bit. So let's say that we have this is our axis of rotation right here. Let me just draw this guy out a little bit more. And so this axis of rotation we're going to call O. And then let's say the center of mass, like I said, it's arbitrary. It doesn't have to be there, but let's say the center of mass is, say here. The distance d is the distance between the axis of rotation and the center of mass. So center of mass there, and then this thing has, you know, mass m, and so its weight is there, and so we have these two components. This component here is the driving force, like a pendulum over here. It's a driving force back and forth. Okay, and let's say that we do d, and since it's d with respect to this pivot point, and angle theta, well, this has got to be d cos theta and d sine theta, right? So d sine theta for all of your dissection purposes. But anyway, this is what it looks like. Where to get a better idea what d is. It's the distance from here to there, or wherever your center of mass is. And it swings back and forth. Yeah, all that. Okay. That's a period of a regular pendulum and the physical pendulum. And our last pendulum that we'll look at is the torsional pendulum. It's like, just imagine that you had a mass, a circular mass. So you can see back in 15.5, a circular mass on a string, vertical. It's hanging vertically, where you can, on the string. You're not looking at it face on plane view, but you're looking at a side view. So it's looking at the width. And then what happens is you can take that mass and just contort it, create torsion or tension in the string, and let it go, and it just bobs back and forth, left to right. But a better picture in 15.5. And that looks like something like this. So, and then it just kind of goes back and forth. So it rotates about angle theta back and forth. Theta, 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 theta. And that formula, 2 pi square root of moment of inertia over kappa, where kappa is some torsional constant, similar properties, physics of the spring constant, the spring. So every string or spring or whatever device it's attached to will have its own torsional constant. And so it's pretty much 15.5. That was, like I said, is just about giving you the formulas. We'll belay the derivations of these periods for some other time. Any questions on any of that? So yeah, we won't need 6 and 7. I mean, it's out of our scope at the moment. Damped and forced oscillations, because we really have to be, well, not only all of us in calculus, but they never cover that. I mean, yeah, I've never seen that, and it's just not included. Not included on the exam. So if you want to get a jump start, it's 10 minutes left. Want to try question 16 of your textbook there, page 442. Something to by these guys. All right, so that, take about, a few minutes to do that, and then we'll close things out. Okay, we got a question. Why doesn't it fully rotate? Because like the spring force, it reaches a maximum and it's trying to get it back to the midpoint. Kind of similar to why the spring doesn't always go all the way up. It reaches a maximum amplitude, and then it comes back. Or sticking with that analog, or that that analogy. So like a mass on a spring, you pull it 2 centimeters down, it's only going to go between 2 and 2. You pull this torsional pendulum 45 degrees, it's only go 45 back and forth. Same idea. Hope that helps you out. Okay.